Hey there everybody, and welcome to the first video on section 7.6. Like section 7.5, the section is split into two videos. The first video which focuses on the solving of the DEs, and the second video which talks about the visuals of these systems. So with complex eigenvalues, you get a different structure to your slope field than we did back in section 7.5 when the eigenvalues were not complex. So the video is split into two parts, just like the previous section. So let's begin this video by talking about the point of section 7.6. So recall what we were doing in chapter 7. We are spending our time solving systems of differential equations which can be really compactly written like this. We saw from section 7.5 that if you want to solve such a system, that really just boils down to, can you understand the eigenvalue and eigenvector structure of A? If you can understand that, and understanding it is a matter of having Wolfram hand it to you, for us. Anyway, if you can understand that, and what you get back from Wolfram are a bunch of real and distinct eigenvalues, then we know how to solve that system. In this section, we just ask, well, what if those eigenvalues are still distinct, but you get some complex numbers in there? That's the point of this section. So here's a motivating example. This is a 2x2 system. The derivative of x1 is supposed to be negative half x1 plus x2. The derivative of x2 is supposed to be negative x1 minus half x2. That can be more compactly written as this matrix equation here. So let's find the eigenvalues and eigenvectors of this matrix. Here they are. This is what Wolfram spit out to me. There are two eigenvalues. In this case, they are complex. And the corresponding eigenvectors that Wolfram gave me, these are representative. There's a family of eigenvectors, but a representative eigenvector for negative half plus I, that eigenvalue, is negative I1. And a representative eigenvector for negative half minus I is I1. Okay, so that's what Wolfram spits out to me. So, is this the solution here? Can we just do what we did in section 7.5? Constant, arbitrary constant, times eigenvector, e to the eigenvalue t, plus another constant, eigenvector e to the other eigenvalue t. Can you just do that? And the answer, just like back in chapter 3, was that from a mathematical perspective, yeah, you can just do that if you don't care about reality or the physical world. And many mathematicians do not, especially in a time of epidemic, Anyway, so there's nothing mathematically wrong about this. It's just this is not useful. Just like back in chapter 3. If you're going to have exponential powers where the powers are complex, what do you do with that if you're trying to model, say, the amount of individuals in a predator species and the amount of individuals in a prey species or whatever, right? Just like in chapter 3, if you want to know where a mass is on a spring, it doesn't help to say that at time 5 I'm at position 3 plus I, right? That doesn't make any sense physically. So just like back in chapter 3, when you have complex stuff like this, you have to somehow boil it down to real valued stuff. You have to take the complex answer and from it distill something real so that you can do things like graph them or make predictions about what physical things are doing. So how do you do that? How do you take complex eigenvalues and from them get some real things? Here is the main result of section 7.6. I think I mentioned in a previous video that at sometimes you will notice parts of my soul dying, and you will notice it here because I'm telling you, I guess. But anyway, there's a lot that I'm sweeping under the rug here. I mean, I know this isn't a theory class, so I don't want to prove everything to you, but I don't like just showing you things without giving some idea where it came from. But that's what I'm going to do now. I'm just going to show you the main result and not really talk about where it came from. You just have to know how to use this, basically. So anyway, so suppose that the matrix A has these two complex eigenvalues. They're conjugates of each other like they always are. So complex eigenvalues come in pairs, just like complex solutions to the characteristic equation in chapter 3 came in pairs. And suppose you got these corresponding eigenvectors. So what you actually can do here is just pick your favorite eigenvalue with corresponding favorite eigenvector. So I've picked my corresponding favorite eigenvector as v1. You could also do this with v2 if you want to. It doesn't matter. Okay, so you pick your favorite eigenvector, you break it into real and imaginary parts. So you write it as a plus bi, where a and b are real vectors. If that doesn't mean anything to you, that's fine. I'll show you an example where I show you how that's done. Then anyway, consider these two functions of time. E to the gamma t, where gamma is from up here, right? Vector a, where a is from here. Cosine mu t, where mu is from there. Minus b, b is from right here. Sine mu t, mu again is from up here. And also this u2, which I won't read to you, but it's pretty similar. It turns out, this is a theorem, that those two dudes are real solutions of this system. So notice they are indeed real. There's no I anywhere in either u1 or u2. These are graphable with like a t-axis, you know, as the horizontal axis. Okay, so the main result is this. Assuming A is 2 by 2, actually this u1 and u2 are like a fundamental solution set. You can grow all the other ones from them. So the general solution of the system is constant times u1 plus constant times u2. So here's the punchline of section 7.6. If you get complex eigenvalues, this is how you handle them. You create this u1 dude like this, create this u2 dude like that, and then you just basically add them up and you can scale them by constants. So anyway, this here, this complex stuff, like what do you do with that? How do you distill from it real stuff? The answer is this. These are real functions. There's a real function, right? And you can add them up and scale them by real numbers. So let's go back to this motivating example. Here's the original data from whatever slide it was a few slides ago. Okay, so now in order to get the solution of this in terms of real functions, you just have to follow the methodology outlined on the previous slide. So on the previous slide, what do you need to do? Pick an eigenvector and break that eigenvector into real and imaginary parts. Okay, so I'm going to pick the first eigenvector, -1i, corresponding to this eigenvalue here, -half plus 1 times I. Okay, so mu is 1 and gamma is -half in this example. Once you pick your favorite eigenvector, you have to break it into real and imaginary parts. That is what I've done here. This vector, -1i, can be written like this. 0, 1, that's a real vector, right? No i's there. Plus -1, 0, that's also a real vector. There are no i's inside this vector, but then times I. Okay, so again, this previous slide says you have to break it into real vector plus real vector times I, and that's what I've done here. Real vector plus real vector I. So I basically just split the i's off from the reals and then pulled the I off of this vector. So notice, if I were to like take this right-hand side and combine it, if I were to do the addition, what do I get? 0 plus -I. That's the top coordinate here. What's the bottom coordinate? 1 plus 0i, which is 1. So that's how you can take a vector like this and break it into real and imaginary pieces. Okay, gamma is -half, mu is 1, a is 0, 1, right? A was this first piece, and then b was the second piece when you broke your eigenvector into those two pieces. So therefore, two real solutions are, this was just the formula from the previous slide. u1 is this, u2 is this. So now it's just a matter of plugging in. So let's plug in. u1, right, so here's the same data, right? u1 is all that stuff, u2 is that stuff. So now I plug in -half for gamma, 1 for mu, there's my A, there's my B, and the general solution is C1U1 plus C2U2. And you're done. So to make that a little more concrete, C1U1 plus C2U2, if you wanted to write that without matrices, let's think about what that is. Because again, the matrix notation is just a way of compactifying things, right? And letting us plug into linear algebra. If I go back to the original system, where is it? Here. The original system, there was no matrix, right? It was just, hey, find me two functions, x1 of t and x2 of t, that satisfy these two equations. So if you want to get back to that with no matrices, it's like this, okay? So C1U1 plus C2U2. Let's think about C1U1. That'd be C1 times this exponential. If you're reading across the top to get x1, I should mention that, you know, x1 is always the top row, x2 is always gotten from reading across the bottom row. Anyway, reading across the top row, I have C1 exponential times 0 cosine. Okay, so that's nothing. Minus a minus, So that's a plus sine. So here is a c1 e to the negative half t times a positive sine. And then you got to keep reading, plus c2, and now keep reading across the top. Again, the 0 here kills a term, and then you have minus cosine. So you have a c2 exponential cosine. What about x2? Now you're reading across the bottom. I have this exponential times 1 cosine, so I have c1 times that right there, added to e to the negative half t 1 sine. And then this 0 here kills that off in the bottom row. So here you go. The x1 looks like this, and x2 looks like this. So unsurprisingly, I think, it's worth mentioning, in Chapter 3, what happened? When you had complex roots of the characteristic equation, you got trig in your answers, didn't you? Suddenly the solution graphs were waving at you. And notice the same thing happens here. Both x1 and x2 suddenly have trig in their answers, and they are waving at you. And furthermore, these are spring-massy kinds of answers, aren't they, right? Because you got decaying exponentials attached to the trig, so they're waving at you, but the action is dying down, suggestive of some sort of system with damping. Okay, so maybe x1 represents the location of mass 1, and x2 represents the location of mass 2, in like a linked spring mass system with two masses. This kind of answer you would see in a damped system like that. Okay, so that's how you handle complex eigenvalues with that theorem that we used on the previous couple slides. Okay, so here's an exercise for you. This system, unsurprisingly, has complex eigenvalues. So I want you to solve this, express your answer with and without matrices, pause the video, and try your hand at that. Okay, so assuming you are back now, let me just walk you through the solution. So you should have gotten this as an eigenvalue from Wolfram alpha and this as its eigenvector. So again, to do this process, it doesn't matter which eigenvalue you pick or eigenvector as long as you're consistent. You can't mix and match values and eigenvectors, but whatever. So I could have done the 1 minus 2i guy and then done whatever the vector was for that. Anyway, okay, so once you pick your favorite eigenvector, you have to break it into pieces. Here's that breaking into pieces right here. So 1 plus 1i is what was in the top, right? 1 plus 1i. And then what was in the bottom? What was in the bottom was 2 plus 0i. So that's how I broke that into real and imaginary parts. So bold A is 1, 2, bold B is 1, 0. And thus the general solution, this is just the theorem. So I just plugged into that theorem like before, is this. C1 e to the gamma t. Gamma is 1 in this example. Here's my A, cosine mu t minus B, sine mu t, and then C2 e to the gamma t. Here's my A, here's my B, and the sines and cosines are swapped places, and instead of a minus, there's a plus there. Okay, so again, so if you don't like this, notation, you should like it. It's nice, but I guess aesthetics is all sort of a matter of taste, right? You can always rate it without matrices, and I guess I told you to do that, you know. So x1, again, we just read across the top. C1 e to the t times 1 times cos t minus a 1 sine 2t with that c1 e to the t still attached, then plus c2 e to the t 1 sine t, c2 e to the t plus 1 cos 2t. So reading across the top row, functions x1 look like that. And then reading down across the bottom row, c1 e to the t 2 cos 2t. That's why there's a 2 right there. And then this 0 kills what's left in the bottom row. And then c2 e to the t 2 sine t. That's why there's a 2 there. And again, this 0 kills what's in the bottom. Okay, so that's how you handle systems like this with complex eigenvalues. In the next video, we'll talk about slope fields for systems that look like this.